Hi, everyone, and welcome to another measurement and instrumentation class. In the previous class, we started power measurements. And for power measurements, we usually need two tools. We need a ammeter and a voltmeter. Sometimes they call it a wattmeter. It's combined. Sometimes it's separate. You have to do it on, yourself. And there are different ways to connect the ammeter, the voltmeter. The voltmeter could be in parallel with the ammeter and the load, or the ammeter could be series with the voltmeter and the load. Depending on what the configuration is, we're going to have some error, obviously, because nor the ammeter nor the voltmeter are going to be ideal. We have some losses in the system, and we can actually measure those losses in our ammeter. And we have different errors that I mentioned in measuring power as well. Now, the main goal usually of measuring power is to ultimately measure energy. Now, energy is the amount of power that we consume or produce in a specific time frame. Electric energy, as you know, is produced by the source of electromotive force, EMF, and which is dissipated in the circuit in the form of heat. Eventually, all the energy is dissipated in the form of heat. Electric energy is converted to heat whenever a current flows through a resistance, and this can be a problem if it makes a device or wire overheat. Usually, if we have high currents, that's going to be a problem. So we want to be able to limit the current as well. That's the reason we use current limiters. Now, the amount of heat that is generated in the system is calculated using this equation. P is equal to IV, and as we know from Ohm's law, V is equal to IR. Therefore, P is equal to V squared over R, or I square R. Now, I square R is known as joules heating, and this is the main reason actually we use transformers as well. So when we use a transformer, usually in the generation side, we use a type of transformer that is called a step up. A step up means we are stepping up or increasing the voltage, and at the same portion, we are reducing the current. Why do we like to increase the voltage when we want to transmit power in long distances? It's because of this equation that you see. You can see here, increasing the voltage is always divided by R. But increasing the current at the same rate, it's multiplied by R. So increasing the voltage is going to have a lower effect and a lower heating effect on the transmission lines than increasing the current. That's one main reason. I don't know if you heard about the war of currents at the early 20th century between Westinghouse and GE, which basically was Edison. Tesla was on one side and Westinghouse and Edison on the other side. Edison thought they should go with DC. Tesla developed AC, and they thought the way to go was AC. And eventually AC won. The reason is that we don't have a DC transformer. If we give a DC voltage to a transformer, you're not going to have anything on the other side. So transformers and everything built around the grid system was AC from that point on. And the main reason is, again, when you have a transformer, you can easily change the voltage and the current, and increasing the voltage has huge benefits. It reduces what they call the joule heating, or the heating in the wires. When the wires heat up, actually, we have an effect called the sagging effect, meaning the wire would become a little soft and they will sag, and they would, have a short circuit, connect to a tree or something, and it's going to be disastrous. And contrary to what the belief is, the transmission lines are mainly made out of aluminum. They're not made out of copper, and they usually have a steel core. Aluminum has a higher resistance compared to copper, so the best conductor that we have right now is gold. Obviously, you don't want to have gold on your wires. If you had that, you're gonna have everyone on one of these poles taking them down. And then copper is so very expensive. So mainly they use aluminum. Still, aluminum is expensive. Some places they take them down and melt them and use them again. Anyway, so I square R is called the joules heating, and the equation for that is going to be equal to P again is going to be I square R. So the standard unit for energy is the joule, but 1 joule is a very small amount of energy for means electricity. So kilojoules, megajoules, gigajoules are sometimes used in scientific work. Now, 1 kilowatt hour, this is very important, is equal to 3.6 times 10 to the power of 6 joules. The amount of energy used or supplied depends on the power and the time for which it is used. Again, energy is the amount of power that we use in a certain period of time. For this purpose, we can measure it in 1 second, 10 minutes, 1 minute, but for electrical power energy consumption, we use hours. So 1 kilowatt hour means we have used 1 kilowatt of power for 1 hour. 5 kilowatt hours, it means we have used 1 kilowatt for 5 hours, or 5 kilowatts for 1 hour, or 10 kilowatts for half an hour. Okay, does it make sense? So if you use 10 kilowatts for half an hour, your consumption will be 5 kilowatt hours. A low power device operating for a long time can use more energy than a high power device operating for a short time. So for example, if you have your dryers are usually 3-4 kilowatts running for 20 minutes, it's going to consume less energy than a 100-watt lamp working for round the clock 24 hours. Okay, so that 3 kilowatts for half an hour, you're going to have 1.5 kilowatt hour of power consumption. That lamp, if it's 100 watts for 24 hours, it's going to be 2.4 kilowatts. So it's going to be 70% more. But it's not as simple as this. Usually electrical companies, I don't know if they recently Xcel Energy has changed your meter. Now I'll show you different type of meters and how they work with digital meters. Those digital meters, they work depending on the time of use, and they have off-peak and peak hour. So usually at peak hours like 3 p.m., I think it's 3 p.m. until 9 p.m., it's around 24 cents per kilowatt hour. After 9 p.m. until tomorrow 3 p.m., it's going to be 7 cents, something like that. So the price is significantly higher during. You can pick that plan. For some people, if you have an EV, you want to charge it overnight, or you want to, it's beneficial, or you want to do your laundry in the morning. But from some people that don't want to do that and they just have limited time, it's better to go with the fixed price. Now, the papers that I gave you, I want you to write your names on it and your buff IDs. This is going to be attendance mainly, but I'm going to grade this as well. So for the first question example, we want to calculate energy for a 60-watt lamp switched on for 8 hours. Pretty simple. And by the way, I want to measure it in kilojoules. And a little reminder that 1 kilowatt hour is 3.6. So 1 kilowatt hour is 3.6 times 10 to the power of 6 kilo 10 to the power of 6 joules. Do you need more time or you're done? Okay, give you a few minutes. By the way, I wanted to make another announcement. Your second exam would be the second week of April. Is that okay? Do you have any exams at that time? I can do first week or second week of April. If you have another exam at that time, let me know. But I prefer, second week of April. I'll put an announcement about that. It's going to be the same format as your first exam. We're going to have a review session as well. You need more time or? Okay, so let's go to the answer. Energy usage is going to be power times the time. Now, power was 0.06 kilowatts, and we had it on for 8 hours, so it's going to be 0.48 kilowatt hours. Multiplying that by 3.6, I'm sorry, 1 kilowatt hour, again, is going to be 3.6 times 10 to the power of 6 joules. So this is going to be 4.8 times 3.6 times 10 to the power of 6. And it gives us 1,728 kilojoules.
That can also be written in megajoules.
Yes, it's going to be 1.7 megajoule. Yes. Well, we asked to write it in kilojoules. Yes, but thank you. Now, second example, we want to calculate energy for a 3 kilowatt kettle switched on for 5 minutes. Yes, again in kilojoules, because energy is, we want to do it in kilojoules, because we want to see how much heat we are. Okay, what did you get? 9,000. 900, 900. Who got 900? Okay, good. Yep. So energy usage is going to be power times the time of usage, which is going to be 3 kilowatts times 5/60, or 1/12 of the hour, which gives us 0.25 kilowatt hours. And when we multiply it, we're going to get 900 kilojoules. Now, next example, the current flowing through an appliance connected to a 120-volt source is 2 amps. How many kilowatt hours of electrical energy does the appliance use in 4 hours? So we're not given the power, we're just given the voltage and the current. Again, pretty easy. And measure this in kilowatt hours. What is the answer? Perfect, thank you. So P is equal to IV, obviously. It's going 2 amp times 120 gives us 240 watts, times the 4 hour, which is going 2.24 kilowatts, gives us 0.96 kilowatt hours. Now, next example, the work done by a heater is 100 joules for a time of 4 seconds, which is 4 seconds. Find out the electrical power of the heater. Has anyone found the answer yet? How much? Yes. So work done by the heater, it's 100 joules. Time taken by a heater, it's 4 seconds. Power is the work divided by the time. So we have 100 divided by 4 gives us 25 watts. Next one, the electric power of the electrical bulb is 50 watts. How much time is required for the electrical bulb to perform the work of 150 joules? What is the answer? Yes, perfect. So we know that P is W over T, or T is P over W. It's going to be 150, or 50 gives us 3 seconds. Now, can I have the papers back, please? Now, the device that measures energy consumptions is the energy meter instrumentation. And what it does, if you think of electricity in the water terminology, imagine you have a water faucet and you have a bucket under it. The amount of total energy you're measuring is like the amount of total water coming out of that water faucet. In other words, it's going to be the integral, which is the summation of VTIT, which is the total power delivered or consumed over an interval of time, T. And VT is expressed in volts and IT is amperes. And sometimes we also call it watt-hour meter or energy meter. Now, this is what comes in mind initially as a energy meter. This is a single-phase energy meter. This is a mechanical one. Newer generations are digitals, but this one has, interesting properties. The digital one, obviously, it measures the current voltage. It has timing. Some of them, the newer ones actually are connected to internet, so they would directly send the data to the power company, and so there isn't a person that comes every month and reads the reading. For these, you need to have someone to come and read the numbers. There are also two-way energy meters as well, and if you install a solar panel on your roof and you want to sell it back, you go to your power company. Some of them allow that, some don't. In California, it's very normal. And they will give you a two-way meter. meaning you can buy or sell energy to the grid. It's going to be a little different. And those are a little bit more sophisticated because it has to, decide which way the direction of the flow direction is and so on. Yeah, Exo also has them. So interestingly, in California right now, you have to be in a line. It's a queue of 6 months, 7 months, 2 years to get that. Because now they have excess energy during the day. A lot of houses have these solar panels on the roof, and the power company doesn't know actually what to do with that power. Building storage is very expensive. Therefore, they won't. So, connecting to the grid, it's going to put extra pressure on the grid. A power grid is very sensitive. It's the biggest machine, human-built machine in the world. Imagine you have thousands, 100,000s of miles just in the US of power lines and transformers. And in a power grid, when the power is generated, it must be consumed immediately. Okay? You don't have a lot of storage to work with. So if you have excess power generated, you must, dump it somewhere. You must be able to consume it somewhere. If you don't do that, you're going to damage the grid. And those damages, if you damage a transformer, it's sometimes millions of dollars, and those huge ones. And you have to wait like 6 months to a year, those huge ones. Small ones are cheaper, like in thousands of dollars, but still it takes a long time. Anyway, let's go back to the analog induction type energy meters. So as it names suggests, it's a mechanical one. It uses coils. It's using the induction method. We have a voltage coil, we have a copper shading ring, and we have 2 current coils. At the middle, we have a rotating aluminum disc, and then we have a magnetic brake. Now I'll explain each one, what's the function of each part. And then finally, we have the gear train to the dials, which shows you the amount of power consumed. So as you can see, it's an energy meter because it's measuring both voltage and current. Therefore, it can measure the power. Now, this is from a different angle, a side cut from that same thing. You can again see the pressure coil. You can just see the brake magnet, the disc, the copper band, the current coil, and the voltage coil. And finally, you have the load connected to the system. And again, this is another cut from the system. When we separated, you can see the copper shading bands, the voltage coil, aluminum disc, and the current coil. And both of them, when they are current, you can see the current coil CC and VC, and that the way that they are connected, and the wiring diagram to the load. Now, the different parts are the driving system, the moving system, the braking system, and the registering system. And the driving system it consists of 2 electromagnets. A coil having large number of turns of fine wire is wound on the middle limb of the shunt magnet. This coil is known as a pressure or voltage coil. So if in the exam we ask what is the pressure coil, it's technically the voltage coil. And it's connected across the supply mains, meaning it's in parallel with your supply. This voltage coil has many turns and is arranged to be as highly inductive as possible and produces a high ratio of inductance to resistance. This causes the current and the flux to lag the supply voltage by nearly 90 degrees. Now, when you have 90 degrees, with them, you're going to have a force that moves the system. The adjustable copper shading ring are provided on the central limb of the shunt magnet to make the phase angle displacement between magnetic field set up by shunt magnet and the supply voltage is approximately 90 degrees. The copper shading bands are also called the power factor compensators or compensating loop. The series electromagnetic is energized by a current coil, which is connected in series with the load so that it carries the load current. The flux produced by this magnet is proportional to and in phase with the load current. Now, the moving system consists of a light rotating aluminum disc mounted on a vertical spindle or shaft. The shaft that supports the aluminum disc is connected by a gear arrangement to the clock mechanism on the front of the meter to provide information that consumed energy by load. The time varying or sinusoidal flux produced by shunt and series magnet induce eddy currents in the aluminum disc, and that eddy current creates the movement. The interaction between these two magnetic fields and eddy currents set up a driving torque in the disc. So as mentioned, they have a 90-degree phase shift, and you have an eddy current on the disc, and these are at the opposite direction. It acts like I would say, a simple motor, what we call an induction motor, something like that. The number of rotations of the disc is proportional to the energy consumed by the load in a certain time interval and is commonly measured in kilowatt hours. So one thing to keep in mind is that the input always have power. It's like an outlet. This outlet that you have here, the voltage is 120. Well, how much is the current coming out of it? 0, because it's an open circuit. So as long as you don't have any current passing through it, you will have 0 power consumption. But you still have voltage. You always have voltage here on demand. As soon as you plug something in, you're going to draw the current. That current with that voltage creates that eddy, the magnetic field, and the opposite field, and starts moving, starts rotating. But the thing is, we still have leakage. So even if you don't consume anything, you may see what we call a creep, a little bit of movement, especially in these analog ones. That's the reason they would calibrate it once in a while, maybe every 10 years. Sometimes they don't do it anyway. And they seal it again because they don't want anyone messing with it and dialing back the numbers. So the braking system is consisting of a permanent magnet. It's the damping of the discs. It provides a damping of the disc by a small permanent magnet located diametrically opposite to the AC magnet. The disc passes between the magnet gaps. The movement of the rotating disc through the magnetic field crossing the air gap sets up eddy current in the disc that reacts with the magnetic field and exerts a braking torque. By changing the position of the brake magnet or diverting some of the flux there, the speed of the rotating disc can be controlled. So basically, it's for calibrating the system, the magnet, and by moving it close or further, you can, calibrate it. The registering system consists of gear train and counter, driven either by worm or pinion gear on the disc shaft, which turns pointers that indicate on dials the number of times the disc has turned. So basically, it's just a counter. The energy meter thus determines and adds together or integrates all the instantaneous power values so that the total energy used over a period is thus known. You can read faster than I can. So therefore, this type of meter is also called integrating meter as well. Now, some problems and errors in these energy meters. The first problem is phase displacement error. The second one is friction error. Any mechanical part has friction. The third one, as I mentioned, is creep. And the last one is effect of temperature variation. So during night and day, you're going to have different values. An error due to incorrect adjustment of the position of shading band results in inaccurate phase displacement between the magnetic flux and the supply voltage. Required coil winding should be designed highly inductive and has resistance, and iron lysis and core are very the resistance should be very small. The inductance to the resistance should be very high. But sometimes that doesn't happen. To avoid this effect, copper shading bands provide around the central limb of the shunt magnet and properly adjusting it by method of compensation. So by adjusting the position of the copper shading band in the central limb of the shunt magnet, this error can be eliminated. So you can take it up and down. Basically, you have another coil with your first coil that compensates for the error. You're giving it a small push. And this actually corrects the phase error and makes it again 90 degrees. Now, due to friction between the spindle and the bearings, an additional amount of driving torque is required to compensate this error by low load adjustment. The two shading bands on the outer limb are adjusted to cause a phase displacement between the enclosed flux and the main flux, which create this extra torque exerted on this. So what they do, they have special devices that they would consume very little power. If it doesn't move, it means you have too much friction. Then they will calibrate that. So it's a very delicate system. You can see, and I'll show you a way to hack it actually at the end. It's very easy. So creep is a phenomenon that can adversely affect accuracy. That occurs when the meter disc rotates continuously with potential applied and the load terminal open circuited. In some meters, a slow but continuous rotation is seen when pressure coil is excited, but with no loads current flowing. So you're going to see a movement, but you're not consuming any power. This slow revolution records some energy, which is creep error. Now, how can we reduce it? By the brake, magnetic brake. We can adjust that. This slow motion may be due to incorrect friction, compensation, vibration, or to stray magnetic field, or for over voltage across the voltage coil. And this shows the shunt magnet pole, the eddy currents, and the disc under the shunt, under shunt magnet pole. It's from the top view. And by applying extra brake, you can get rid of the creep. So it's a delicate balance between not creeping and also not the friction not allowing it to move that much. Now, the effects of temperature, both driving and braking torque equally. With the increase in temperature, the resistance of the induced current path in the disc is also increased, and so produces negligible error. A flux level in the brake magnet decreases with the increase in temperature and introduces a small error in the meter reading. This error is frequently taken as negligible, but in modern energy meters, compensation is adopted in the form of flux divider on the brake magnet.
In the summer.
Yeah. So actually, it's sometimes better to make it hot. But that's a negligible error. As mentioned, it's not that much. A better way actually, and I'll show you, to make it stop without opening it. There's an easy way. Testing of energy meter, we have the RSS Phantom. Yes, a huge one. You need a big one. And you need it at the proper, you need and you need it at the right place. It's going to magnify the brake magnet and it's going to stop the movement. So if you have a huge magnet, put it at the right place, it's going to stop the movement. But it's obvious it's not going to work in the digital ones. Digital ones are, Now, energy measured by energy meter is going to be N1 over K1. Energy measured by the RSS meter is going to be N2 over K2. The percentage of error is going to be N1 over K1 minus N2 over K2 over N2 over K2 times 100%. So the energy meter constant K is defined as K is the number of revolutions over the energy, which is N over E revolutions per kilowatt hour. In commercial meters, the speed of the disk is of the order of 1,800 revolutions per hour at full load. By the way, the reason that they use this, but you may ask why they still use it. It's cheap. It's very durable and reliable. It lasts like 30, 40 years with minimal maintenance. Digital ones, may, blow up or something, but these are very reliable. And if some of those digital ones go out, it's going to disconnect your power. You don't want the power to be disconnected in the middle of the night. So if you go into a power plant, you can see that mostly all the energy meters are using these integrating meters. Now, example number one, if a 240 single phase watt-hour meter has correctly adjusted having a meter constant of 600 revolutions per kilowatt hours, determine the speed of the disk for currents of 10 amps at a power factor of 8.8 lagging in 1 minute. So energy consumed in 1 minute, E would be VI cosine of theta times T. Revolutions in 1 minute is going to be E times K. So you can solve it using this easily. You already have V, you have I, you have cosine of theta. What is cosine of theta? It's 0.8. It's your power factor. You can just easily replace it and find parameters. Now, an energy meter revolves 100 revolutions of disk per unit for a unit of energy. Find the number of revolutions made by it during an hour when connected to 20 amps at 210 volts and 0.8 power factor leading. I'm going to put these example as your homework for the upcoming week. If energy meter revolves 350 revolutions, calculate the percentage of error. Again, we have the voltage, the currents, the cosine of theta, and we have the revolutions in here. We want it for an hour, and we can calculate that easily. Now, the third example, we want to explain in brief why energy meter reads energy while watt meter does not. An energy meter has a registration constant of 100 revolutions per kilowatt hours if the meter is connected to a load drawing 20 amps at 230 volts and 8.8 power factor for 5 hours. Find the number of revolutions should be made by it if it's actually made 1800 revolutions. Find the percentage of error and explain it from consumer point of view. Now, the reason that a watt meter can't measure power because it doesn't have memory. That's the simple answer. It can measure power instantaneously, but it cannot add it during a period of time. If a power meter has type of memory, it's a digital and it has a memory RAM or something, and it adds all those together in a certain period of time, and it's not built for that. It's not built to be turned on for a long period of time. Then it could act like an energy meter. So an energy meter is fitted with some type of registration mechanism whereby all the instantaneous reading of a power are summed over a definite period of time. So an energy meter can read energy, whereas a watt meter indicates the value of power at a particular instant when it is read, and hence it can not read energy. Registration constant here is 100 revolutions per kilowatt hour. I is 20, V is 230, and cosine of theta is 0.8. Again, I'll give this as a homework so you would calculate. I wanted to actually give it as a quiz, but we don't have enough time. I want to finish this. So measurement of power and energy, just a summation. The transformers used in connection with the instruments for measurement purposes are referred to as instrument transformers. They are classified as current transformers used for current measurement and potential transformers used for voltage measurements. These transformers are used not only for extension of the range of the instrument, but also for isolating the instrument from a high current or voltage. So that's the reason we mainly use transformers. It acts like a breaker as well to protect the device. Single range instruments can be used to cover a wide range. Indicating instrument can be located at some distance from the circuit. This is a great advantage, particularly for high voltage situations. Now, the problem with these analog instruments, if it's connected, for example, to your generator and you're at the operating room or something, the control room, you need a system to be able to read that measurements instantaneously. So that's the problem with analog systems. You cannot have remote control and remote measurements over that. And that's actually a benefit of relays and contactors, and I'll explain about that later on. So by use of CT with split core or hinge core, the current in heavy current bus bar can be measured without breaking the circuit. This is one way to measure the current. Again, you can use a split core transformer, but another way is to use a clamp system as well. But for very high voltage systems, clamp systems do not work. Therefore, it's like taking a sample from the current. Okay, that's it for today's class. Again, your second exam is going to be the second week of April, and unless someone has an exam or something, you have an exam. And I'm going to post a set of homeworks this weekend, and you're going to have 1 week to turn them in. Thank you so much, and have a great weekend.